Okay, we talked about bonding last time, and it was probably two types of bonding. We have again ionic bonding. And remember, ionic bonding always could be sort of determined by what you have sort of coming together to make that bond. And it always should be a metal and a non-metal. And because of some of those, again, periodic trends that we talked about, when those two things come together, what always ends up happening is we do get a transfer of electrons from the metal to the non-metal. Again, the result of that is our metal will then become a positively charged ion, which is our cation, and our non-metal will become our negatively charged ion, which would be our anion. And it is those charged ions that are now attracted to each other through electrostatic attraction. Again, no sharing of electrons happening here. And obviously something like sodium chloride there is an example. Sort of the other version of bonding is covalent bonding. And covalent, much like ionic bonding, could also be recognized by sort of what it's involved within the bond. And that is always going to be kind of two nonmetals. And because of their periodic trends, they both, again, do not want to give away their electrons. They really want to gain electrons. So as we talked about, really the best that they'll sort of do is share. And with a covalent bond, we do have sharing of electrons happening. And as we talked about, that sharing of electrons can be one of two things. It could either be sort of equal sharing of electrons, and equal sharing of electrons is what's known as a nonpolar covalent bond. And within that sort of situation, we expect the electron to sort of spend an equal amount of time near both of the nucleuses. And overall, as we talked about, you could kind of think of a nonpolar bond as kind of being really like a neutral bond. There is no, again, sort of positive side to that bond, no negative side to that bond, as they're sort of sharing electrons equally. When we have unequal sharing of electrons, that creates what is known as a polar bond or a polar covalent bond. And the result of a polar bond is we do have somebody, one of the atoms within the bond, that's really going to be more electronegative. And electronegativity, as we talked about, is the ability of an atom to bring electrons towards itself. Remember, it increases as you go up and to the right on the periodic table. And the result of that difference in electronegativity means that the electrons within the bond that's being shared will kind of spend more time near one of the atoms versus the other. And it's going to spend more time, thank you, near the more electronegative atom. And the result of that is you will actually get some charges formed within the bond, these sort of partial positive charges, partial negative charges. The partially negative part of the bond would be near the one that's more electronegative, where the electrons are kind of moving towards. The one that's more partially positive would be the least electronegative sort of atom, where the electrons are sort of moving away. And remember that you can kind of represent it, as we saw with our HF, one of two ways. And a lot of times it is represented with this dipole arrow. And again, that dipole arrow really points to the side that's more negative in the bond. And as we talked about, kind of the other side there, that again, if you kind of look at it, it kind of looks like a plus almost going through there. That is the side that is more least electronegative as well. And again, that creates these, as we talked about, partially negative charge and partially positive charges on each of those atoms. They are partially positive, partially negative, as we talked about, because again, there is still sharing of electrons happening here. So nobody has completely let go of the electrons like what happens in an ionic bond, where we completely sort of have transfers of electrons and ions being formed. Here again, there's some aspect of sharing that's happening, and that is what's going to give us those partially charges. And that is different than what we saw, obviously, in our nonpolar situation, where we had, say, two Fs, because they are both basically the same element in this case. We would expect them to be shared equally. Now, one of the major ways that we could kind of determine whether or not we expect, sort of a polar bond, a non-polar bond, or even an ionic bond in some sense, is we do use, as we did last time, the difference in electronegativity values. So again, we could calculate the difference in electronegativity values. And remember that those values run from 0 to 4, where 4 is the most electronegative and not so much there on the 0 side. And if you do the difference in electronegativity, and again, you get anywhere from like 0 to 0.4, it is typically usually considered a nonpolar covalent bond. We're going to share electrons equally. If you're above that 0.4, like 0.5 to less than 2, it typically is going to be some type of polar bond happening in that case. And as we talked about, usually above 2, and it's not perfect, that kind of 2 number here, you do typically will get more of an ionic bond. And really, as we talked about, a couple of things when you're trying to maybe determine these things. Once again, you really don't need the electronegativity values for ionic, as we talked about. As long as you can identify you have a metal and a non-metal, that definitely should be an ionic sort of bond that's happening. In terms of nonpolar and polar, again, you can a lot of times just use the general trend in electronegativity. Remember, if you're kind of comparing two atoms that are within a group or within a period on the periodic table, you can pretty much make a pretty good effort that they are going to be a polar bond because they are in different locations within the group or different locations within the period. The only things you do have to watch out for is a couple of situations on the periodic table, especially with the electronegativity values, that you do have, again, that diagonal relationship in terms of electronegativity, where, again, one element may be further up, but one may be further to the right, and they do sort of cancel each other out in terms of their values, like nitrogen and chlorine, I think we maybe looked at the other day, and maybe carbon and sulfur also has that sort of diagonal relationship as well. So it definitely is possible to end up with two different elements that may possess the same electronegativity value and also will share the electrons sort of equally. Typically speaking, when we look at changes in electronegativity values, we are looking at bond polarity, and really all we're looking at is between these two atoms making this bond, are they going to share their electrons equally or unequally? In most cases, that's not going to tell you if the entire molecule is going to be polar or not. The only time that will be, as we touched a little bit upon last time, is if there's only one bond. So obviously, if there's only one bond in the whole thing, whatever that bond is what the molecule would be as well. We finished up talking about drawing Lewis structures, and remember, when we do draw Lewis structures, we want to think about how things are put together. So remember that the least electronegative usually goes in the center. We want to count the total number of valence electrons. Remember as well, if you come across something or you're drawing a Lewis structure for something that does have a charge, you do have to take that charge into account in terms of your kind of electron total. If something has a negative charge, you do need to add some electrons to the total. If something has a positive charge, you do need to kind of subtract electrons from it. Once you do that, again, as we talked about, basically what you want to do is just sort of make one single bond from the center to each of the outside atoms. Remember that each of these lines represents 2 electrons, so all the remaining electrons should always go on the outside atoms first, and they should be put on as dots, pairs of dots. And again, as you move around the outside atoms, we're looking to get everybody to 8 electrons. As we talked about, the whole purpose of bonding is for everybody to reach the same electron configuration as the noble gases, right? So that is sort of the goal here. If you still have electrons after you fill out the outside, you then go to the center and you pop those guys on also as pairs of electrons. At some point, you should be out of electrons, especially when you get to the center atom. The last thing you want to do is just to make sure everybody has met the octet rule, except for, again, hydrogen that could only have 2 electrons, should never have more than 2. And it's really at that point, as we talked about, that if somebody has not reached the octet rule, then what you want to do is try to fix it by making a double bond. And if by some chance the double bond does not fix the situation, then you want to kind of go to a triple bond. Remember that if we are going to double bond something, so let's just say in this example, we only had that going on. and we're a little short here on the center atom, remember to make the double bond or even to make a triple bond if necessary, we are actually taking a pair of electrons and again moving them in to do so. And again, that is going to get us everybody to the octet rule, still maintain our proper number of electrons. And obviously, if that did not fix it, you could look for another double bond opportunity, or if there is not one, then you would go to a triple bond. Remember, you do not want to kind of double bond or triple bond right out of the box. You also don't want to, when you're drawing Lewis structures for covalent bonding, you don't want to think about the electrons belonging necessary to any particular element. You just want to kind of distribute all the electrons as equally as you can to everybody, and that's the better sort of approach. Any questions on any of that stuff there? Okay. So let's continue on here. We're talking a little bit about bond length, and not that you have to memorize any of these numbers here, but just in general, this is the bond length between, say, some double bonds, single bonds, and triple bonds. And if we look at the bond between carbon and carbon, single bond, double bond, and triple bond, we can see that the single bond is 154 picometers long, 133 and 120. If we look at the carbon nitrogen relationship, single bond 143, double 138, and triple 116. So the general trend that we see is every time you sort of put on another bond, as you go from a single bond to a double bond to a triple bond, the distance between the two atoms gets smaller. And if you think about it, to make a double bond or a triple bond, you're putting a lot more electron density between the two atoms, and that's going to bring everybody closer to each other. So those more negative charge between them is going to draw everything in tighter, and the single bond is going to typically be longer than a double bond, and a double bond is going to be longer than a triple bond as you continue to kind of move that negative density, electron density between the two atoms. So in general, as I mentioned, triple bond is really the shortest, and double bond and a single bond is the longest out of all that. A double bond is not like twice as long as a single bond, and a triple bond is not like 3 times as long. But the general trend is that the more time you kind of make more bonds, the shorter the distance becomes between the two atoms within the bond. They're just basically pulling things together. Now, in terms of strength, that also relates to strength. So typically speaking, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. And that also has to do with obviously a lot more electron density. Things are closer to each other. It is not, again, 3 times as strong a triple bond or anything like that, but that's the general trend as well. I think of it like a pencil, right? If you had a brand new pencil, ish, like this guy, you would have no problem snapping it in half, right? You take like a chemistry exam, you're left with like a nub in there and an eraser, right? Super hard to try to break that guy or hold on to the pencil. So very, very small, right? If you ever try to break something that's super small, very, very hard to do that. Again, everything's just very close to each other and held very tightly in that situation. Now, we're not going to talk too much about resonance structures, but we did touch upon it as we were drawing some of our Lewis structures. And in general, resonance structures sort of develop in situations where really one Lewis structure doesn't sort of adequately describe sort of what's going on. And that usually involves when double bonds are formed. And as we saw, I think we did nitrate, if I'm not mistaken. So when we did nitrate, we did need to make a double bond to one of the oxygens. And remember that since all of these oxygens are equivalent to each other, we really could have double bonded any one of the three here. And that meant that in addition to this picture, we could also have double bonded to the right, which would have gave us this Lewis structure. We also could have double bonded there, obviously, to the left, which would have gave us this Lewis structure. Let's put the right thing in the middle there. And all three of these structures are resonance structures of each other. They are all usually separated by that sort of arrows. And again, it's because not one structure could sort of adequately describe what's going on. Those double bond electrons, again, are sort of what are referred to as being delocalized. They're really moving around. So at any given point, again, they could be on the oxygen on the left, they could be the one on the right, they could be on the one on the left. And the true structure is probably somewhere between any of those things. And that allows you to draw sort of equivalent Lewis structures, which are known as resonance structures. Um, So again, if you were asked to draw something like this, you would not necessarily have to draw all three of those unless you were specifically asked to draw all the resonance structures. Any one of the three would be fine. But basically, you think of it as, okay, there's more than one place where I could do the double bond. So I could do it to the left or the right. Here's another example, ozone. Again, you could have double bonded on the left oxygen, or you could have double bonded on the right, and it gives us two equivalent sort of structures. All right. That's carbonate as well, which I think we might have drew as well. Again, very much like nitrate, could have double bonded there, or double bonded there. All right. We're not going to worry about this one. All right, so now we're going to talk about some of the exceptions to the octet rule, and these are exceptions to the octet rule, which means even though we always want to try to get things to 8, there definitely are some exceptions to that. I will say right off the bat for our class, you should never ever draw an exception. We will always obey the octet rule in this class. But you should be aware of what the exceptions are. When you go to 1A, you'll do nothing but like exceptions, a lot of exceptions you'll draw when you go to 1A. But for here, everything's going to behave the octet rule. But we're going to talk about some of the exceptions to it. The first exception is an incomplete octet. And there are some atoms which are actually perfectly fine with less than 8 around them. Beryllium, aluminum, and boron are typically the ones that you see. And boron is the one most often that you will sort of see. And when we look at boron here, I'll just redraw it over here since it was getting cut off. Boron is okay with less than 8 electrons around it. It's got 6. It also makes it sort of electron deficient, which helps it in some situations be something known as a Lewis acid, a really good Lewis acid in that case. So I would say boron, probably the most common one that you will come across, but not in here and in future classes probably. Again, beryllium, aluminum also included in there, even though technically they do more of ionic bonding. Some other exceptions to the octet rule. Whoops. It's an odd number of electrons. So it is possible that when you add up everything, so for example, if we look at NO, nitrogen monoxide, nitrogen has 5 valence electrons, oxygen has 6, that's 11, which means we are going to end up with 1 unpaired electron. So it is possible to get some things that have an unpaired electron. And that's an odd electron number, sometimes referred to as free radicals sometimes. And those things are very, very reactive because, frankly, they have an unpaired electron. So they want to try to kind of correct that situation. And up in atmospheric chemistry, you get a lot of chlorine molecules that have that, and they're very, very reactive because of that unpaired electron. Once again, we will not come across any of those. You should not draw any of those in this class, or the previous one as well. Again, everything should obey the octet rule. Probably the most common exception to the octet rule that you will see, definitely when you go to 1A, is the expanded octet. And much like there are some elements that are okay with less than 6 around it, there are some that are perfectly good with more than 8 electrons around it. And if you look at the periodic table right around our friend sulfur, and you kind of go to the right, to the left, and down in the nonmetal region of where sulfur is located, those are the ones that typically can do an expanded octet. And the reason they could do an expanded octet is something that we will talk about when we do chapter 11, which ideally they assume maybe you did that before you did 12. But when we talk about electron configuration and energy levels, where sulfur is really on the 3rd energy level. So if that period where sulfur is on the periodic table is the third energy level, or the n is equal to 3. And because of that, that is where our d orbitals, which is where some electrons are housed, that is where they basically first start to begin. And they do have those orbitals available to them to sort of stash the extra electrons, and they're able to go over 8. Yes, sir.
The reason a lot of things work is because either have a full valence shell or an empty valence shell. Boron is 3 valence electron, so it makes sense why it would have 2 bonds.
Yeah. So yeah, that is true. So in terms of the expanded octet, because they have these d orbitals available to them, anything starting sort of where sulfur's period is located and sort of down, they also have those d orbitals, and that allows them to, again, accommodate these sort of extra electrons. That also means, just for future reference, if you go above sulfur on the periodic table, things like carbon, nitrogen, oxygen, and so forth, they're actually on the second energy level. And on the second energy level, there are no d orbitals, so they can never go over 8. So those guys like carbon, nitrogen, oxygen, fluorine, and that sort of row can never do the expanded octet. So something like SF6, and I won't draw all the electrons on the fluorine, but all of those fluorines have electron dots around them. But if we just look at the relationship here between sulfur and its bonds, it has 1, 2, 3, 4, 5, 6 bonds. Each of those bonds are 2 electrons. So in this sort of arrangement, sulfur has 12 electrons around it, which once again is not a problem for it because it got some room to sort of stash those electrons as well. That is also why if you search the internet, which you shouldn't, no. If you search the internet for Lewis structures and pictures, you sometimes will come up with some pictures that in this class you should not draw, because we do not go over the octet rule in this class, but can actually draw. So an example of that, for example, is if we took SO4 minus, and we just went through our sort of Lewis structure steps here. Sulfur is 6. There are 4 oxygens. Each are 6, and it has a -2 charge, which means we do want to add 2 electrons. So that's 24, 26, 32, I believe there. In this case, sulfur is going to be in the middle. Oxygen is going to be around. We're going to do a single bond to each of them. That gives us 2, 4, 6, 8. And then we're going to add the rest of our electrons, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. At that point, based on our sort of rules here and obeying the octet rule, we have a perfectly fine structure here for sulfate. Now, if you go search the internet, or when you get to 1A, you may actually see sulfate drawn like this in sort of its expanded form. And here, obviously, sulfur has gone over 8 electrons, and it's actually perfectly fine, that picture as well, but not fine for our class because we're obeying the octet rule. So, you know, if you go look up stuff on the online and have somebody do it for you, you might end up with that picture. Your teacher would definitely know you did that, right? Because we're not doing that in this class. So you do want to obey the octet rule in here. In reality, though, as you will learn in probably Chem 1A, when you talk about formal charge and stuff like that, based off of formal charge, the guy on the right actually is the better Lewis structure than the one on the left. So this is actually a situation where double bonding it up actually does, based on formal charge, get you a much better sort of picture than you do on the left. But for our class here, we are going to, again, obey the octet rule. So everything you draw in here should obey the octet rule. You just need to know what the 3 exceptions are. You won't be asked to draw any of them or come across any of them, but you should know what the 3 sort of exceptions to octet rule are. Any questions on that? All right, we're going to talk now about geometry and molecular geometry. And molecular geometry deals with sort of the 3-dimensional structure of these molecules. Their sort of orientation in 3-dimensional space. Now, when we talk about geometry, there's really 2 types of geometry that we're going to discuss in this class. And it is based on the idea of how many bonds there are to the center atom and how many electron pairs there are around the central atom. Those are the two main things for our geometry that we're going to talk about. And there's two types of geometry, as I mentioned. One is what is referred to as the electron pair geometry. And for the rest of this, I'm just going to call that the EP, electron pair geometry. So I have to write it out a bunch. And that describes sort of the three-dimensional arrangement of how the electrons are around the central atom. The other type of geometry that we're going to talk about is the molecular geometry. And sometimes people refer to this as the shape of the molecule. And this describes the geometry of the molecule as a whole. So not just how the electrons are arranged, but the result of what electrons are present, what bonds are present, and what ends up happening with actually how the atoms move and where they end up, the overall actually shape of the molecule. Now, as we will see in certain cases, both of these names are going to be the same, and in other cases, one will be the same and one will be different. So there's certain cases where they are actually the same name, same situation, and in other situations they are different. Now, if you draw a good Lewis structure and you understand basically that when we do geometry, it's all about the center atom. So when we do geometry, it's all about what's happening in the center atom of your structure or your Lewis structure. That's really the most important thing. And the idea of why we sort of get different geometries is this. Ultimately, when we make bonds, it's involving electrons. And that means no matter what you do, because you got all these bonds happening, you're going to have electrons near electrons. And electrons are negatively charged, which means when you get negatively charged electrons near other negatively charged electrons, technically speaking, they don't really want to be near each other, yeah, because they're both the same charge. So what's going to happen is they're going to try to get as far away as possible from each other, but they can only go so far because they are bonded to some things. So they can only escape each other as far as possible. So this is how we end up with some different geometries is sort of, all right, we're just going to kind of keep moving until we get like a happy medium place where we're far enough away from each other to sort of be okay. And that gives us the different sort of geometries that we end up with. The sort of name of this idea is what's known as VSEPR. It's the valence shell electron pair repulsion model, hence the abbreviation. And when we talk about the geometry, it's really broken up into two categories. It is a category where you draw your Lewis structure and you look at your Lewis structure. And once again, as I mentioned, it's all about the center atom is the most important one. When you look at the center atom, you do not see any lone pairs or non-bonding electrons. So remember, lone pairs are non-bonding electrons. They're the dots. So you draw your Lewis structure, you look at the center atom, and you basically got no dots. Yeah. Now, the other type of one is when you do draw your Lewis structure, you do have non-bonding electrons on the center atom. So you basically have dots, right, on the center atom. And again, it's always the center atom. And it's really the only thing that you should look at when you're doing geometry. So sometimes people will go to do geometry and they start looking on every atom that's, in the picture. You always want to go to the one in the center. Now, it is definitely possible that you could have more than one center atom. So it is possible you could have more than one center atom in a particular molecule. You will actually just do this geometry for each one individually. Just kind of break it up, kind of put your hand over one side and do it for this guy, and then kind of go the other way and do it. I would say in this class, most of the time, you'll probably have just one center atom, but it is definitely possible to have multiple kind of center atoms in a molecule. The one super important rule when you're doing geometry, and really only when you're doing geometry, is this: pretty much everything counts as one. It doesn't matter if you have a single bond, doesn't matter if you have a double bond, doesn't matter if you have a triple bond, doesn't matter if you got a pair of electrons as dots. Everybody here counts as one electron pair, and one bond. Unless obviously it's the dots. So I'll take the dots out of there. But basically, if you got a single bond, double bond, or triple bond, when you're counting everything, you should count it as one electron pair and one bond. Again, only when you're doing geometry. If you're asked some regular question, non-geometry related, of how many bonds you got going on, then obviously you can answer it normally. But for geometry, single bond, double bond, triple bond, it counts as one electron pair and one bond. The second one is not going to be too important for our purposes here since we're not going to do too much resonance structures. But if you were to draw all three of like those resonance structures we just drew for like nitrate, you could do this geometry for every single structure. And you usually will get the same geometry for each structure that you draw. All right, let's just start with the simplest by far geometry that you could do, and that is a diatomic molecule. And in a diatomic molecule, you basically only have two things bound to each other. So in a diatomic molecule, there really is not a center atom. In order to have a center atom, you need at least three. So in a diatomic, there's really not a center atom. So as soon as you see a diatomic molecule, the geometry is always going to be linear. The only way to arrange two things is in a straight line, right? So 2 points, straight line between them. That's always going to be the geometry. It absolutely does not matter if it is a single bond, a double bond, a triple bond, two of the same thing, two different things. Doesn't matter. Everybody here, the geometry is going to be linear. So the simplest geometry you could have is basically two things that are bonded to each other. Again, the number of bonds, the type of bonds does not matter. They will always arrange themselves in a straight line, and you always get this linear geometry. Any questions on that one there? All right, so obviously when we have three or more atoms, there's a few extra things we have to look at. And let's talk about what happens when we have three or more atoms involved. Our first example will be this beryllium chloride. And once again here, there's really two things you want to look at, and there's two geometries we're going to talk about. Again, it's going to be the electron pair geometry, or that EP, and the molecular geometry, or the shape. All right, so the first thing you want to do is have a properly drawn Lewis structure. Obviously, this one missing a few dots here on the outside. We'll maybe pop some on there. But really, the only thing that's really important when you're doing this is the center atom. So we want to go to the center atom. And there's basically two things that we want to look at to help us decide. And that is how many electron pairs there are. So when we look at this, there's an electron pair there, an electron pair there. So that is two electron pairs. And we also want to look at how many bonds there are. And in this case, there's one bond and two bonds, and there are two bonds in this case. And those are the two sort of things you want to look at when you're trying to determine geometry. Now, the number of electron pairs, this number here, will give you the electron pair geometry. So whatever number you come up with for that is going to tell you the electron pair geometry. And the electron pair geometry is this. Because you only have two electrons pairs, they do not want to be near each other. They're going to move as far away as possible from each other, and they're going to end up on opposite sides of each other. And that's going to give you a linear geometry for that. And because these are bonded atoms or bonded electron pairs, the atoms are attached to those electrons. So as the electrons move away from each other, so does the actual atoms in the molecule. And they also end up in the same geometry known as linear. It has a bond angle that you do need to know of 180 degrees. So this is going to give us a linear geometry for our electron pair geometry. And because the atoms are attached to it, they're going to go as far away from each sides of the end of the center guy. And that will give us our bond angle of 180 degrees. Any questions on that there? All right. The next example is a center atom with three things attached, like boron trifluoride here. And once again, we're going to go to our BF3, and it's all about the guy in the center. And again, the guy in the center here, in terms of electron pairs, has one electron pair, two electron pairs, three electron pairs. And bonds has one bond, two bonds, and three bonds in this case. Once again, as I mentioned, it is the electron pairs that tell you the electron pair geometry. And what happens in this particular case, as you can kind of see, is we now have an extra bond that we did not have in the previous one. So these guys are going to try to stay away from each other. These guys are going to try to get away from each other. But now these two guys can't get too close to each other either. So because we now have that extra bond in there, it gives us an electron pair geometry known as trigonal planar. And some people will call this triangular. Now, once again here, because all these are bonded electrons, the atoms that are attached to it will actually follow suit. They will just follow in the same sort of pattern because they are bonded to them. So as they are moving, so are the atoms. And our molecular geometry in this case, or our shape, will also be trigonal planar. It again is sometimes called triangular because if you look at it, it will make a triangle. Yeah, so make a nice little equilateral triangle that will sort of happen in sort of three dimensions. It does have a bond angle here of 120 degrees. So once again, you do need to know bond angles for this class. So bond angle, bless you, 120 degrees in this case. Any questions on that one? All right, so again, three electron pairs, three bonds, trigonal planar for electron pair geometry, trigonal planar for molecular geometry, bond angle of 120 degrees. The next example is something where we have a center atom and four things attached, basically, like methane. And once again, if we take a look at our center atom here, we are looking at how many electron pairs. So it's got 1, 2, 3, and 4 electron pairs. And it has also 1, 2, 3, 4 bonds as well. Once again, the electron pair is going to tell us the electron pair geometry, which in this case is what is known as tetrahedral. Or tetrahedron if you find an old book. Once again, what happens is we got one more bond that we didn't have in the previous one. So now everybody also needs to kind of keep away from each other. So again, these guys got to keep some distance. They got to keep some distance. They got to kind of keep some distance. Our molecular geometry of our shape, in this case, will also be what is known as tetrahedral as well. And it will have a bond angle of 109.5. And as you can see, maybe a little bit here in this picture, let me erase what I wrote over it. It sort of makes like a triangle on the sides and maybe a little pyramidal type of shape towards the bottom, but we do get this sort of 109.5 degree bond angle. Once again, the electron pair geometry and the molecular geometry are both the same name. The reason, again, that all these examples we just have done, all three of them, the linear, the trigonal planar, and the tetrahedral are all the same name for both of them, is because when you look at the center atom in each of these cases, there are no dots. There's no non-bonding electrons. They're all bonding electrons. And that means as the electron pairs move, so does the atom. So the overall shape of the molecule ends up being the exact same shape as the electron pair geometry, because as those electrons move, the atoms go for the same ride. So if you draw a Lewis structure and you look at your center atom and there are no dots on the center atom, the electron pair geometry name and the molecular geometry name should be the same name. Yeah, they should be exactly the same because you have only dealing with bonded atoms. Any questions on that? Now, obviously here, if we start introducing some non-bonding electrons to the center atom, we are going to start to see some differences in the name. And the name that's affected in terms of non-bonding electrons is actually just the molecular geometry name. So the molecular geometry name, as we sort of introduce non-bonding electrons to the mix, is the name that changes. The electron pair geometry will still be the same, and it's still based on how many electron pairs you have. So that name will not change. It'll be one of the same names we just ran through, and that will stay the same. But the molecular geometry will change. Why does it change? It changes for a couple of reasons. One big reason is there's not an atom bonded to those non-bonded electrons, so it's got a little bit more room for movement. And secondly, because of that, they want to get away from each other, and there's not an atom in the way, so there is a little bit more room that they can move away from each other, and that creates a different shape than what we see with all the atoms being present. Now, the major issue that happens when we start to have non-bonding electrons involved is we get some differences in electron and electron interaction. And as we talked about, they do not really want to be near each other because they are negatively charged. That means that there are sort of like it's okay-ish situation to I really don't want to be near you. So the kind of okay-ish situation is the less repulsion, the less movement away from each other occurs when you have bonding near bonding. So in your Lewis structure, that's like lines near lines. That's an okay situation. That is all the situations we just talked about, basically. We have just bonded atoms. The next situation, which is getting not so good, is we have non-bonding electrons near bonding. So somewhere in your Lewis structure, you'll have dots near lines, and they do not want to be near each other. They're going to try to get away a little further than they can. And once again, they can escape a little bit more because there's not that bonded atom involved in moving around as well. The worst situation in terms of electrons being near each other is non-bonding near non-bonding, are dots near dots. That is a situation where they're going to try to get as far away as possible from each other. And they could kind of do that because they're now missing maybe a couple of atoms not in the way. They got a little extra strength. And once again, as these non-bonding electrons try to move away from each other, all the bonding electrons that have the atoms will also move away because they don't want to be near them. And again, that's what's going to cause the molecular geometry name to change. And we're going to end up with a different shape that basically occurs. So let's take a look at some of these examples. If we draw the Lewis structure for sulfur dioxide, which I think we did the other day, it will look something like this. And once again here, we do want to focus on the center atom. And when we look at the center atom here, which is the sulfur, the number of electron pairs in this case is one electron pair there. One electron pair here. When you're counting electron pairs, doesn't matter if they're lines or dots, you're just counting pairs. And now I come to my double bond, which should count as how many electron pairs? Should just count as one. So that was that rule that we talked about. Single bond, double bond, triple bond. When you're going around doing geometry and you're counting electron pairs, they're all essentially one. So this double bond here will count just as one electron pair. So that's going to give us 3 electron pairs. And as we talked about earlier, it is the number of electron pairs around the center atom that determines the electron pair geometry. So the electron pair geometry we already know because we saw something earlier with 3 electron pairs, and that is still going to be trigonal planar. But now when we look at the number of bonds in this case, we have 1 bond there, and once again, the double bond will count as only 1 bond. So again, it counts as 1 electron pair and 1 bond there. That's a total of 2 bonds. So what happens in this case is we have these non-bonding electrons here, and these guys go, I want to get away from them. So they're going to come down, but they can't get too close to each other either as they come down because they got to also keep some distance between those bonding electrons. And it ends up with a molecular geometry. I personally go with angular. I will say books go with bent. are bent angular, some books. But for here, I'm going to go with angular, but again, some people will use bent for this one. The reason we won't use bent is we'll talk about in just a second as to why we don't see that. And what we end up with is a bond angle of less than 120. So the bond angle is always based off of the electron pair geometry. So what ends up happening in this case is we do get something like this. And again, what that does is it allows those non-bonding electrons and bonding electrons to keep some distance. But as I mentioned before, we still have to keep some distance between those bonding electrons. So as those bonding electrons move away from the non-bonding electrons, the atoms that are attached go with it, and it starts to basically bend or get this angular type of shape that ends up with a bond angle of just less than 120 degrees. Any questions on that? The next example is something like ammonia here, NH3. Once again, taking a look at the center atom, number of electron pairs. We got 1, 2, 3, and 4 electron pairs. Once again, doesn't matter if there are dots or lines, we're counting everybody, and everybody gets counted as one. Number of bonds in this case, 1, 2, and 3. So once again, the electron pairs tell us the electron pair geometry. Something with 4 electron pairs is tetrahedral. Now, in this case, we do have the situation of bonding electrons near bonding, non-bonding near bonding. But in this case, we actually have an extra atom that we didn't have in the last one. So as they start to move away from each other, we will end up with a molecular geometry known as trigonal pyramid or pyramidal. And that's sort of what happens. Again, these non-bonding electrons, everybody's going to definitely want to get away from them. But now these guys can't get too close to each other because they also need to keep some distance because, again, we're putting electrons near electrons. And it gets this trigonal kind of triangle and a pyramidal sort of shape happening there at the bottom. And it's known as trigonal pyramid. It has a bond angle of less than 109.5 degrees. It's about 106 or 8 in this particular case. Now, this is a good point to talk about two geometry names that we've talked about, which is trigonal pyramid and the one we saw earlier with 3 electron pairs and 3 bonds. That is trigonal planar. They are different, yes? One is a triangle shape, one's more of a pyramid shape. They have different bond angles. They are not the same geometry. So when you are doing an exam or a quiz, do not just write trigonal, yeah, and let me choose, because I'm going to choose an X, yes, because I don't know chemistry, so make sure you choose the actual name there. Or my other favorite, I'm super confident with trigonal. I'm super confident with the P. Oh, clearly that's like planar. I mean, pyramid. Which one is it? That's clearly what I wrote there, right? So you cannot just write trigonal. You cannot just write trigonal with a P and unlegible writing afterwards, right? So you got to make sure you choose pyramid or planar. Again, they are different. So you can't just say trigonal as a blank ending of that. Let's go back here since apparently I lost one. So let's do the last geometry here, which I'm not sure where it went on my page, but let me just clear it out. The last geometry you'll be responsible for in this class is a situation like we see in water. And this is, if we take a look at it in terms of electron pairs, we have 1, 2, 3, and 4 electron pairs. Again, because it has 4 electron pairs, we know the electron pair geometry going to be tetrahedral. It has, in terms of bonds, 1 bond and 2 bonds in this case. Now, in this situation, we have pretty much all the worst case happening. We have bonding electrons near bonding, we have non-bonding electrons near bonding, and we have the worst situation, non-bonding electrons near non-bonding electrons. So those are like all the bad situations. And those non-bonding electrons near non-bonding electrons are going to try to get away from everybody. And what happens is, in this case, we get these non-bonding electrons here going as far away as possible. And that's going to cause these bonding electrons with the atoms to also keep a pretty good distance. And again, they can't get too close to each other there because they got to also keep some distance. And we end up with a molecular geometry known as bent or V-shaped, which is why you typically will see water drawn in this V-shaped or bent-shaped when people draw it, because that is the geometry associated with it. This has a bond angle of less than 109.5 degrees. This is also why when we did SO2, we're going to use angular to distinguish between angular and this bent, because the SO2 angular is less than 120. This guy's less than 109.5. So again, they are different. This bent versus, say, the bent in the other one. So just to distinguish it for our class, we will use angular for the SO2 example and bent or V-shaped for this situation here. Any questions on that there? Good news, bad news on this. Most people can't visualize three-dimensional space in their head, so this is definitely just a memorization type situation. Yeah, best way to do it is memorize electron pairs, number of bonds, and the geometries that go with it, and they do want you to know the bond angles, so just kind of memorize that kind of thing. And here's a table from your book or similar to your book, and again, gives you your electron pair geometry, molecular geometry, number of electron pairs, the central atom, number of bonds. So again, really just knowing these two and the geometries that go with it is really kind of the easiest way to kind of do it. And that's actually the one from your book more similar to it. So again, you are responsible for this name, the bond angle, and the molecular geometry name as well. And again, electron pairs bonds is kind of the way to go. I also made a table, I think, that should be on Canvas, that kind of just is similar to this and kind of talks about bonding and geometries and that type of stuff. Any questions? So I guess the classic, hey, you should know. No. All right. All right. The last thing we're going to talk about here in terms of bonding is molecular polarity. So earlier on in this chapter, we talked about bond polarity. And again, bond polarity is when we use the difference in electronegativities to talk about just between these two atoms, as we did earlier, are we going to get a polar bond or a non-polar bond to occur? Now, a dipole moment is basically, for a molecule, the overall representation of unequal sharing. So when you look at a molecule as a whole, if there's unequal sharing of electrons, it will have a dipole moment. And if it has a dipole moment, it will be a polar molecule. Non-polar molecules will not have a dipole moment, which means overall, in terms of the entire molecule, they are sharing electrons equally. So again, here we're really looking at molecular polarity. And if you have a polar molecule, it will have a dipole moment. Now, how do we represent a dipole moment? Well, we represent it with the same arrow that we did with our bond dipole. And this is a dipole moment overall for the molecule, where this guy points to the more negative side of the molecule, and this side, the more positive side of the molecule. And again, only polar molecules will have a dipole moment. And much like our polar bonds or non-polar bonds, if we have a polar molecule, that means when you look at that molecule, there is a side to that molecule that's more positive, and there's a side that's more negative. And if you have a non-polar molecule overall, again, you could think of it as like a neutral molecule. There is no like positive side or negative side to that molecule. Let's talk about the simplest molecules to decide whether or not the molecule is polar or nonpolar. The absolute simplest ones to do molecular polarity on is diatomic molecules. And when you have a diatomic molecule, as we talked about, it basically only has two atoms involved. And if we took something like a homonuclear diatomic molecule, which is a fancy way of saying two of the same atoms attached. So if I have something like H2 here, and I just asked you straight up, H2, this bond, is this bond polar or nonpolar? This bond is going to be a nonpolar bond, hopefully, right? Again, they have equal sharing of electrons. If you did the difference in electronegativity, you would get a difference of 0, which means it is a nonpolar bond in this case. So this is a nonpolar bond. Now, when we look at something like H2, it absolutely only has one bond in the entire thing. So because this thing has only one bond in the entire thing, and that one bond is a nonpolar bond, that would mean that this molecule here is also going to be a nonpolar molecule. Because frankly, it has just one bond, and the only bond in the whole thing is nonpolar. It's going to be nonpolar. So this is the place where I was talking about earlier that bond polarity, where you do the difference in electronegativity, and molecular polarity will be the same, because in a diatomic molecule, there's just one bond, and if that bond's nonpolar, the thing's got to be nonpolar because there's no other bonds involved. And the same thing would happen if you had a heteronuclear, like a heterogeneous mixture, two different things. We know from talking before that this bond right here is a polar bond because of the difference in electronegativity. You got a difference in electronegativity of approximately 1.9, which is definitely polar. That means that this molecule is also going to be polar because there's only one bond present, and that bond is a polar. We could draw our dipole moment on this guy very simple because it should be heading in this direction towards the fluorine is the dipole moment. The fluorine is more negative in his side, and this side is more positive, the hydrogen. So the simplest ones that you could do in terms of molecular polarity is diatomic. By the way, again, does not matter if it's single bonded, double bonded, or triple bonded. If you had O2, which has a double bond, that's a nonpolar bond. And again, it would be a nonpolar molecule. So again, doesn't matter if single bond, double bond, or triple bond. All you have to do is identify that bond. And if it's polar, the molecule is going to be polar. If it's nonpolar, the molecule will be nonpolar. And again, that is specifically only for diatomic molecules where you have only two atoms. Now, if everything was that simple, that would be great, but hey, it's not. So when you have three or more atoms involved, you have to look at a couple of things. So if you have three or more atoms, you have to look at, are there polar bonds? And you also have to look at the molecular geometry. And take a classic example. We'll take a look at CO2. And if we look at CO2, the first thing that we should know is it does contain polar bonds because I have carbon and I have oxygen, and I don't even need the numbers in this case because carbon and oxygen are on the same row on the periodic table, and oxygen is further to the right on the periodic table. So just because of the placement of those two, I know that the carbon-oxygen bond should be polar without even needing my numbers and doing my differences. It should be polar. And because oxygen is further to the right there, when we look on the periodic table, oxygen should be more electronegative, which means if I drew my bond dipole arrows very badly there, they would be pointing towards the oxygen in this case. So something like this, which is CO2, does have polar bonds. So you may say to yourself, it has polar bonds. It probably will make sense that this molecule would be polar. But the second thing that we have to look at is actually the geometry. And if we do our molecular geometry here, we go to our central atom, and the electron pairs on our central atom, double bond counts as one, double bond there counts as one. So that is 2 electron pairs. Number of bonds, 1 electron pair, sorry, 1 bond, 2 bonds. So something with 2 electron pairs and 2 bonds has a molecular geometry of linear, about 180-degree difference there. Yeah. So what we have in this situation is CO2, and we have a linear geometry like this pencil. And basically we have carbon in the middle, oxygen on the sides, and we basically have this oxygen pulling this way, the electrons, but we have the oxygen on the other side pulling the other way. And I am actually pulling really hard in opposite directions. My pencil is going nowhere, right? So my pencil here, if I pull in opposite directions like they are going nowhere. So this is a prime example that although CO2 does have polar bonds, because of its geometry, they actually cancel each other out. And this is actually a non-polar molecule because of that. Now, if you look at something like water, and we look at the central atom here, our polar bonds, there is polar bonds heading towards the oxygen in this case, oxygen being further to the right there, more electronegative than hydrogen, and we do have polar bonds. If we look at the geometry as we just did on the very last one, our central atom again has 4 electron pairs and 4 bonds, and that's going to give us our bent, our V-shaped geometry. So what happens in this particular case is now instead of it being a straight line, we got something like this happening. We got polar bonds coming this way and this way. And you could kind of think of this like a string or a tug of war, like everybody's meeting here on top. And if you visualize like a string on the top and we just pulled from the top, this whole thing is going to basically move. And what ends up happening is we do get a net dipole moment that occurs here in water because they actually add to each other. And the oxygen side is more negative and the hydrogen side is more positive in this case. Now, why is that? Well, when we look at these bond dipoles, they are, as they say in physics, vectors. They have direction, they have magnitude. I fell asleep at that point, but I woke up at the point where in some cases these vectors will add to each other, and in some cases they will cancel each other out. And typically speaking, if you have vectors that are heading in equal and opposite directions, they cancel each other out, kind of like pulling on a rope equally. Nothing's going to happen. Or if they're heading right at each other, also will cancel each other out. If you think about like a swinging door that kind of swings open both ways and you have somebody on each side pushing equally, door's not going to open either way, right? It's just going to kind of stay there. So if you have these kind of guys going at each other, equal and opposite, or away from each other, equal and opposite, they will cancel each other out. If they are not going equal and opposite away from each other, they could add to each other, which is actually the case you get over here in water. You got a vector going that way, a little head to tail action, and then they actually add up heading in that direction there. I fell back asleep at that point. It was a bad day. So it is definitely possible to have polar bonds in something, but because of its geometry, it can be a non-polar molecule. Nobody ever in this class, right, in chemistry, wants to do that. Otherwise, we would be in a physics class. So we don't want to add vectors. We don't want to think about vectors. We don't want to do any of that stuff. So there must be an easier way that'll get you through probably 99.9% of the time. And there is. So the easy way to sort of do molecular polarity when you got 3 or more atoms involved is basically this. There are some symmetrical geometries. and some symmetrical geometries for our purposes here, and these are molecular geometries we're talking about, is trigonal planar and tetrahedral. I think that's all you got in here, tetrahedral. And what these have in common is if you draw the Lewis structure, no dots on the center atom. And if you have that situation and all the outside atoms are the same, it is going to be a nonpolar molecule, most likely. So if you had something like this, and you draw like a little Lewis structure like so, you go to the central atom, and all you have to look at is no dots. Everything on the outside is the same, nonpolar. Done. This is going to be a nonpolar molecule. Now, what would happen if we took this guy and we swapped out one of the fluorines for a hydrogen? And we pop a hydrogen in there. Now what we have is the same polar bonds. And by the way, there are polar bonds, obviously, in this guy. And there are polar bonds in this guy. But now by swapping out that hydrogen in there, carbon-hydrogen is actually a nonpolar bond, right? It is actually 0.4. So it is actually not pulling in any direction. So now when you think about it, if you think about like a rope going out to everybody, you got 3 people pulling on one side, the other guy just kind of just hanging on, not really pulling in the opposite direction. You could imagine that these guys over here are going to kind of pull a lot more than the other guy. And actually, he's going to actually, reality, kind of pull that way a little bit himself. He's going to actually push with them. And you're going to get some movement that's going to happen. And now it goes from being a nonpolar molecule above to a polar molecule in this case. So if you draw a Lewis structure and you have no dots on the central atom, everybody on the outside is the same, nonpolar. If you draw a Lewis structure with no dots on the central atom, everybody on the outside is not the same atom. Pretty safe bet you're now in a polar molecule. So that's a really quick way to kind of do that. There are some unsymmetrical geometries. Which for you guys would be angular, trigonal pyramid, and bent are V-shaped. And what these all have in common are there are dots on the center atom. And if you have dots on your center atom and all the outside atoms are the same, going to be polar. So again, if you took something like our water, I see dots on the central atom, I see outside atoms are the same, going to be polar, this guy. I take this guy here, my SO2. I see dots on the central atom. I see everything on the outside is the same, going to be polar. I take my NH3 that we drew earlier. I see dots on the central atom. Everybody on the outside is the same, going to be polar. So that's like the super quickest way that you could probably do molecular polarity and probably get it right. Yeah, dots or no dots. The only one this leaves you is linear. And that's basically an easy one to figure out because it's a straight line. So in a linear situation, if they're going opposite of each other, nonpolar, they're going right at each other, polar. But if everybody in terms of their electronegativity is heading in the same direction, like one person pulling on the rope will become polar. So it is possible for that to happen. So again, you can see that you could pretty much do molecular polarity really quickly. You know, some of the other ones that we drew earlier, we had something like this. I won't draw all the dots. No dots on the central atom, everything on the outside the same. Going to be non-polar in this case. Yeah, so again, very quickly, you really could do that. And again, the diatomic, you can figure out as well. I think maybe we also drew, we had this guy, right? We drew this one earlier on as well, again, with not all the pluses. Once again, no dots, everything the same, going to be polar. if I had this, and again, I'm not drawing in all the dots on the outside, guys. Should this be polar or non-polar, this one? It should be polar. No dots, but everything on the outside is not the same. So instead of non-polar, this will be polar in this case. So that's like the quickest way that you could do molecular polarity and probably get it right, I suppose. Yeah. Any questions on that? All right, like I said before, up on Canvas, you will find a little handout I made of a table of the geometries, the bond angles, all that stuff you can know. Also, a little bit on there, it talks about how to quickly do like the molecular polarity and all that kind of stuff. So make sure you check it out as well. Any questions on that? I think that wraps up this chapter. Okay, we're going to continue on here. We're going to pick up next chapter. So we're going to go to chapter 5. We're going to talk about naming and nomenclature. So we're going to talk about all the different types of ways to name things in this chapter. They are based off of the really different types of sort of bonding and compounds we've been talking about. There's sort of two categories. There's obviously ionic, as we've been talking about, which is between a metal and a non-metal. And then there's more molecular or covalent, which obviously is between two non-metals. And depending on sort of what you got going on, will determine how you go about naming things as to whether it's sort of an ionic compound versus a molecular compound. So let us get into it here. So there are certain things that do sort of go by common names, and these you should always sort of call by their common names. Um, H2O is water. It's not a trick question when you see it. Just put water. Don't put like dihydrogen monoxide or any of those weird things. NH3 is ammonia, not to be confused with something we'll see a little bit later on, which is ammonium. And CH4 is your simplest organic molecule you could have or compound, and that is methane. So these guys typically do go by their common names. Everything else sort of has a formal sort of way that we name things. And when we talk about naming compounds, again, as I mentioned, it does revolve around the two types of sort of compounds that we talked about with bonding. We have ionic compounds, which again is our metal and non-metal, and our covalent, or again, molecular compounds, where we're going to have sharing of electrons versus transfer of electrons. Now, when we talk about naming metals and non-metals, which is really going to give us the ionic compound situation. There's really two ways that we sort of name things in this situation, and we touched upon it a little bit, I think, in chapter 4 as well. Because it's an ionic compound, because we had a transfer of electrons, we obviously will have two ions that have been formed. We will have our positive ion that's formed, which is our cation, and we'll have our negative ion that's formed, which is our anion. And as we talked about there in chapter 4, always in sort of when you write the formulas for an ionic compound, and also when you name an ionic compound, it is always the positive guy first, then the negative guy second. So it's always both in formula form and name form. We always go positive cation first, followed by the anion. So that's always the order at which you want to do that. Now, just the ions alone, and you want to maybe just name the ions alone, as we talked about in that chapter. A reminder that if we have a positive ion like H plus or Na plus or Ca2 plus, any of these sort of positive ions, we basically simply just use the whole name of the element. So this would be the hydrogen, and then we would just basically put ion at the end of it. This would be the sodium ion, and this would be our calcium ion. So anything that's really a positively charged cation, we always just basically use the whole name of the element, and we do put ion at the end. If you are asked to write the formula for any of these cations, that is what they should look like. It should be the symbol and it should have a charge. So if you're asked to write the formula for an ion, that name ion, by the definition of it, is it should have a charge. And that means when you write the formula for it, you should include the charge. Now, our negatively charged guys are anions. Remember, these are our negative guys. You could have something like H minus, for example. You could have Cl minus, O2 minus. The negative guys, we actually use this first part of the name, but we do replace the last part with the IDE ending. So hydrogen is one of the only elements that can kind of go both ways. It could be positive, it could also be negative. And if you have the negative version of hydrogen, which usually happens after it comes after a metal, that is not hydrogen. That is known as the hydride, IDE ion. Cl minus is not chlorine, but it becomes the chloride ion. And O2 minus becomes oxygen, becomes the oxide ion. So things that are negatively charged get the IDE ending at the end of it. And again, same idea. If you were asked to write the formula for an anion, that would imply it should have a charge, and you should write something like Cl minus, O2 minus, and you should include the charges. The other thing that we talked about there at the end of that chapter was what happens again when we put a positive ion together with a negative ion. And remember, as we sort of touched upon in the bonding chapter, the purpose of that is for everybody, right, to reach the noble gas configuration in terms of their electrons. So whenever we put something together, like if we took a sodium ion and we put it together with an oxide ion, we do want to put it together in a way that we always end up with an overall charge of 0. So in this particular case, we have +1 here, -2 here. That means we need not 1, but we need 2 of those sodium ions. That's going to give us a grand total +2 to balance out the -2 that's over here. And if we just count up, we got 1 and 2 sodium. So when we wrote to write the formula, sodium with a 2, and we have 1 oxygen and an oxygen here. Now, when we write and put together our formula for an ionic compound, it should never have a charge. So when you put the two ions together, positive and negative, you want to put it together in the simplest way possible to get to 0, and the overall formula should not have a charge. But you should remember that it is actually made up of things that do have charges. So when we see the formula Na2O, we should know that that thing is really these 3 ions, basically. It's made up of these 2 sodium ions and the 1 oxide ion. But again, when we put together the formula, always should have no charge, the actual formula, but made up of something that does have charges. Any questions on that? So when we talk about type 1 and type 2 compounds, these are always ionic compounds. And these are always meaning then that you have a metal and a non-metal. And the first thing that you should know or sort of remember when you're thinking about naming is the most important thing is this guy. So whenever a metal is involved and you want to name something, it is ultimately the metal that's going to determine how you go about naming it. So the metal is really the most important thing in terms of how you should name it. Now, when we talk about metals, there's 2 types of metals. There's ones that are sometimes referred to as type 1 and ones that are referred to as type 2 metals. Type 1 compounds contain a type 1 metal. And what a type 1 metal is a metal ion that is going to be positive, that has a fixed positive charge. So if you remember from the periodic table, the groups that have fixed positive charges for metals, That means if your metal comes from group 1, group 2, group 3, are the three exceptions that we talked about in the transition metal region, zinc, cadmium, or silver. Those are all going to be type 1 metals. And the good news about that is there's a straightforward way of naming that particular compound. You actually don't have to do any extra work with that because they have fixed positive charges. So as we talked about, sodium will never have a +2 charge, +3 charge. Sodium is pretty much locked into +1 always. And in terms of naming, that means you don't need to tell people, hey, this is sodium with a +1 charge. You could basically just say, hey, it's sodium. So that's a really good thing. Now, type 2 compounds, it again is the metal that's the most important, and it is the metals that can have a variable charge. So if you have a type 2 compound, it has a type 2 metal, it can have a variable positive charge. So as we can see down here, chromium in some cases could be +2 or +3, copper +1, +2, iron in certain cases +2, +3. And it does depend on the situation. And usually where we find these metals located is our transition metals. So those guys in the middle between group 1, group 2 and group 3 on the periodic table. So this is usually a transition metal, obviously except for the 3 above, are just to the right under the staircase. Like lead, tin, etc. in that area. So usually these guys, again, are in this area. And then obviously we have our staircase coming down, and also just to the right there is typically where we find those guys. Now, what is the deal with those? As we'll talk about, because they can make a different charge depending on the situation, you have to tell people when you name it, hey, in this case, we're talking about copper with a +1, or hey, we're talking about copper with a +2. And you don't need to do that with type 1 because it can only form one type of charge. So it's just known that is the charge it should have. Any questions on that? So here's a table from your book again. You can see all the positive ions there. Basically just going to use the whole name of the element. And you can see our IDE there for our negative guys. Again, the negative version basically of our nonmetals up there, top right of the periodic table. So let's talk about how we go about naming type 1 compounds. Like I said before, type 1 compounds, again, is going to be metal and nonmetal. It's going to be ionic. That's the most important thing. That, again, is going to come from group 1, 2, 3, silver, zinc, or cadmium. So the good news is when you see that, here's how you name it. All you have to do is take the whole name of the metal. And then, frankly, all you have to do is take the non-metal, drop the last part of the name, and replace it with the IDE. So whole name of the metal, non-metal, drop the last part, drop an IDE, maybe a little bit more than the last part in some of the elements, but you drop the IDE in there. So that is, again, how come we get our NaCl, metal, non-metal. Sodium, when I look at the periodic table, which is the metal, the most important thing, I look at the periodic table, I see it's in group 1, which tells me it's a type 1 metal. And really at that point, once I know it's a fixed positive charge, I don't need to do anything else with this. All I have to do is follow my rule, whole name of the metal, which is sodium. Chlorine gets the IDE treatment, and we end up with sodium chloride. I take a look at CaBr2. Once again, Ca is calcium, which is a metal. Br is a nonmetal. And again, it is the metal that's most important. I take a look at the periodic table. I find calcium hanging out there at number 20 in group number 2. And that also tells me it's a type 1 metal. It has a fixed positive 2 charge. So that is a type 1. And that's all I need for this. I'm just going to give the name, whole name of the metal, calcium. The non-metal gets the IDE treatment and it becomes bromide. So this is calcium bromide. By the way, this is not calcium dibromide unless you like an X. No prefix here, yes. People always want to put prefixes here. This is not the place for prefixes. There is a specific place where we use prefixes, and this is not it. The easy way to remember not to use the prefix is this. If you have a metal and you're using a prefix, you're doing it wrong. Yeah, so usually you got a metal, you should not be using a prefix in that name at all. So if there's a metal involved, do not use a prefix. There's only 1 or 2 instances where that might occur, and that's because the name of the other guy actually has a prefix in the name. It's not because you added the prefix. The name of the things actually has a prefix in it. So good way to remember, you got a metal, don't use a prefix for sure. It doesn't matter how many of those BRs you have. Frankly, it doesn't matter how many of the calciums you have. You could have 400 calciums there, it would still be called calcium. And you still have 300 bromines, it would still be called bromine. I don't know what you would have in that case, but again, it doesn't matter how many of either of those things you have. There should be no prefixes used on any of this name at all when you're doing this. The reason, obviously, we have the 2 there is for what we talked about earlier. Obviously, calcium is group number 2, which means it has a +2 charge. And bromine, as we talked about earlier, group number 7, it should have a -1 charge. And again, when we put this together, we do need an extra Br to give us a -2 to balance out our +2 in this situation. And again, no effect on the actual name in this case. Any questions on that? And as we talked about earlier, remember that when we do put it together, we want to do it in the simplest way possible to get no charge. And once again, if we take a look at this, which is Ki, good thing to do is run through what you got. So that is a metal, that is a non-metal. That automatically tells you this is ionic. Then you should look at the metal always. Again, K is group number 1 on the periodic table. So that is K plus, which is a type 1 compound. And that again is all you need. So you're just going to go with the whole name there of our metal, which is potassium. This guy goes from iodine to iodide, IDE at the end of it. And you end up with potassium iodide. Again, Ki, no charge together, but made up of a cation, that's K plus, and an anion, that is I minus. And again, you just need 1 of each of those, and that's why we get to 0 with the formula Ki. Any questions on that there? All right, so why don't you name some of these here? Actually, I'll change that since I did that a second ago. Why don't we put, let's go MgCl2. Why don't you also give the formula for these? Let's go with aluminum oxide. Let's go with calcium nitride. And let's do lithium chloride. All right, so names on the left there, formulas on the right. There's take a look and see. So once again, if you're naming, a good thing to do is just to identify sort of what you're dealing with. So when you take a look at the first one here, potassium is a metal and Cl is a non-metal. So once again, that should always check off we're dealing with an ionic box here. And once we have the metal involved, that's again always the most important thing. So when we look at the metal, which is potassium, we can see it's group number 1, which means it's a type 1 metal. It has a fixed positive charge obviously of K plus. Cl is group number 7, right, which has a -1 charge. So all we have to do is start with the whole name here, potassium, and a little chloride IDE at the end for that particular one. Any questions on that? Taking a look at the next one, zinc is a metal. Sulfur is a non-metal. Once again, going to check the ionic box. Taking a look at our metal, it is a transition metal, but is one of those three that does have a fixed positive charge, the zinc, cadmium, and silver. So it does check off, again, our type 1 box. So a reminder that just, I think we went over in the previous chapter, but just to remind everybody, right, when we look at the periodic table, right, everybody in group 1 has a +1 charge, everybody in group 2 +2 charge. 3, 4, 5, 6, 7, and 8. +3 here at aluminum. Again, we got our staircase coming down. -3 for group 5, -2, and -1. And remember, here in our transition metal region, these guys are usually, again, a variety of charges, but our zinc and cadmium +2 and our silver +1. So again, those are our sort of type 1 guys. Obviously, everything else through here and then down into here, that's going to be a type 2 variable type of charge sort of going on in that situation. All right. So again, zinc, even though, as I mentioned, is a transition metal, it is one of those fixed ones. So that is all we need in this case. So it's just going to be zinc and then again, sulfide IDE at the end of it. Once again, our cation here is zinc with a +2 charge. Sulfur being group number 6 has a -2 charge. So again, one of each of those balances out. Once again here, magnesium metal, chlorine non-metal, that checks the ionic box. Magnesium group 2 checks the type 1 box. So now we could just proceed to naming. So magnesium whole name and chloride IDE at the end of it. This obviously, our cation is magnesium with a +2. And remember that our chloride is Cl minus. It is not Cl2 on the bottom minus on top. Again, the 2 on the bottom means you have not one, but 2 of those. So if you were asked to write the formula for the anion in this case, Cl minus is what you should write. You should not write Cl2 on the bottom minus on top or anything like that. Yeah. All right. Lastly, barium and hydrogen. Metal, non-metal, actually, in this case. And barium being our metal, group number 2, fixed. So this is going to be barium. And hydrogen here is actually coming second after a metal. That is the negative version of it, and that is hydride. So our cation in this case is barium with a +2, and our anion is actually H minus in this case. And again, that is the negative version there of hydrogen. Any questions on any of those names? Again, no prefixes or anything like that in this situation. All right, so we're going to go formulas here, and we want to, again, put it together in the simplest way possible to get to 0. Really what you want to do when you're doing this is just think about the basic ions that make this up. So obviously you can see aluminum and oxide. That's aluminum, which is a metal. Oxide is oxygen, which is a non-metal. So again, that tells you ionic. That also should tell you these are ions. So we want to go to the periodic table and just get the ions that should be here. So aluminum, which is group number 3, would have a +3 charge. Oxide, which is oxygen group number 6, would have a -2 charge. We're looking for a common number to get this to 0. You can multiply the two numbers together, get 6, and that's going to get us to 0. So now at this point, all you have to do is figure out how many of each you need to get to 6. So for aluminum, I need another one. And for oxygen, I need another couple. And that's going to give me plus 3, which is plus 6 to balance out my minus 2, minus 2, minus 2, minus 6 in this case. Now I have my formula. I have 1 and 2 aluminums. And I have 1 and 2 and 3 oxygens. And I end up with Al2O3. Now, I personally think it's better to kind of think about it this way and put it together this way. Some people are taught to just bring the charge down for the subscript and kind of cross it over. It will work like 95% of the time. It will not work 100% of the time. You will get some wrong answers along the way. So if you just want to kind of just do it without thinking and do that, you can. 95 is not too bad as of a score. But there definitely be a lot of situations where that will not give you the right answer. So it's best to maybe think about it the right way and just try to balance things out so you hopefully do get it. Calcium, metal. Nitride, which is nitrogen, is a nonmetal. So again, that tells you it's ionic. Calcium is group number 2, so that means it should have a plus 2 charge. Nitrogen is group number 5, which means it has a minus 3 charge. Once again here, common number is 6. To get our calcium to 6, we are going to need 3 of them. And to get our nitrogen to 6, we are going to need 2 of them. So 1, 2, 3 for the calcium, and 1 and 2 for the nitrogen. And we end up with our correct formula here. Any questions on that there? Lastly, lithium metal, chloride nonmetal, ionic. Lithium group 1 is plus 1. Chloride group 7 is minus 1. We just need one of each of them in this case, and we will end up with LiCl. Any questions on any of those there? So this is type 1, just basically whole name of the metal, IDE for the nonmetal, nothing more that you pretty much have to do. All right, let's talk then about type 2 compounds. As I mentioned before, type 2 compounds will contain metals that can make different positive charges depending on the situation. And because of that, if you've taken a lot more chemistry classes all the way through organic, you will learn that basically naming is just about telling people exactly what's there, basically. You're just kind of telling people, this is what we're dealing with. So because the metal can have more than one type of charge, you have to do an additional sort of step to tell people what metal you're dealing with. What is the charge on the metal? So type 2 will also be an ionic compound, which means we will have a metal and a nonmetal. And once again, whenever the metal is involved, that is the most important thing. Again, going to be mostly your transition metals, or just again to the right underneath the staircase. So here's the deal. When we look at something like FeCl2, we do have a metal, we do have a nonmetal. And when we look at our metal, we see that it's dead center almost there in the transition metal region, number 26, I think, up there. And that should signal to you that this is a type 2. And with a type 2, the good news is we pretty much name it the exact same way as we do type 1, but we just have to add an additional thing to the name to let people know what the charge is on the metal. So we will still be doing our whole name of our metal. We will still be doing our non-metal, where we drop the last part and put the IDE. The additional thing that we do in between is a Roman numeral. And people always screw up on the Roman numeral because they not sure what it means. So what the Roman numeral means is not how many metals you have. It is the actual charge, the actual positive charge. If you took one of those metals out by itself, what would the positive charge be? And that is what the Roman numeral represents, the positive charge on the metal. So how can you figure that out if it can make multiple charges? The good news is whenever you have a metal that's in this situation, you will always know the charge of whatever it is attached to. So whatever it's attached to, you will know the charge of, and you can kind of work your way backwards to figure out what its charge should be. So if we take this example here, I have an iron, which is a type 2, which means maybe I don't know what the charge is at this point. But the one thing I do know is Cl, and Cl is group 7 on the periodic table, which means it does have a -1 charge. There's not just one Cl there are two, which means overall, my negative part of this guy is -2. The thing that we know about ionic compound formulas is when we put it together, everything should add up to 0. So in this particular case, we only have one iron that needs to balance out the -2 charge from those chlorines. That means that it must have a +2 charge in this situation. And you can always figure out what the charge is on your metal by looking at the charge of what it's attached to. That, frankly, is all we need to figure out for our name. We will go whole name of the metal, which is iron. We're going to go Roman numeral number 2, not for how many irons we have, but for the actual +2 charge that it has. And much like in the first one, there is still a metal in this name, which means I am not going to use a prefix or anything like that. This is just going to be chloride. Does not matter how many of them that you have there. So this is going to be iron Roman numeral 2 chloride. Again, the Roman numeral indicates the charge if you took one of those metal ions out, what the positive charge is. Question on that there. So why do we need that? We need that because we could have something maybe like this, FeCl3, right? And FeCl3, same situation, metal, non-metal. Iron is a type 2 metal. So in this case, we have iron and we have chloride, not one, not two, but we actually have three of them, giving us a -3 in this case. And that would mean that the iron in this case is not +2, but will be +3. And the name of this guy would be iron Roman numeral 3 because of the charge. And again, chloride. So because iron could have multiple types of positive charges, you need to tell people when you give the name, hey, in this case, we're talking about iron with a +3, or in this case, we're talking about iron with a +2, and that is what the purpose of the Roman numerals are for. Questions on that there? All right, so why don't you take a second here and try to figure out what the name of this is. That PB is lead. Again, lead is a little bit to the right of transition metals, but underneath the staircase. So it is a type 2 metal. So what would you come up with the name? Take a moment. Okay, so if we take a look at it, obviously lead is a metal. Oxygen is a non-metal. So that tells us it is a ionic compound. The lead, like I said, if you look on the periodic table, not exactly in the transition metal region, but just to the right underneath the staircase, which tells you it is going to be a type 2 situation. And that means because it's a type 2, we do need a Roman numeral. So for sure here, we're not sure maybe what the lead's charge is, but we do know oxygen is group number 6 on the periodic table, which means it has a -2 charge. And there are two of them, which means if we add that together, that is a -4. That means in this particular case, our lead has a +4 situation. And this would be lead Roman numeral 4 oxide. And again, the 4 is for the charge. Now, a lot of people will go, hey, that's lead 2 oxide because they'll do the crossover move I was talking about a second ago, where they'll just like, hey, take the 2 up there and the 1 over there, and you will get the wrong answer. Yeah. And so again, if you want to do the crossover move, it doesn't work 100% of the time, but it will work a lot of times, but it will not work in every situation. Any questions on that there? Now, there is a older system of naming, and we're really not going to use that in this class, but you do still come across it occasionally in books and labs and stuff like that. But there's an older school for type 2 where we do not use Roman numerals, and we use more of the historical name for the elements, and it either ends in ic or ous, the name. Ic is typically IC, the one that has the larger positive charge. OUS is the one with the smaller positive charge. So iron 3, or the iron 3 ion, would be called the ferric ion, while the iron 2, which is the smaller positive charge, would be called the ferrous ion. And FeCl2 would be called ferrous chloride. But it does, especially for iron and copper, people still like to use those names a lot. But for us, we will strictly use the Roman numerals. But in case you see it along the way, that is a thing. And here's a table from your book that kind of shows you some of those older sort of ways of naming. But again, we're not going to use that in this class. We will use the Roman numeral name. Now, one other kind of weird Roman numeral situation that occurs with an element is actually mercury. And if you look at mercury, you have a mercury ion that looks like this, +2 on the top, 2 on the bottom. And you have a mercury guy that looks like this, just +2 on the top. Oddly speaking, the one with all the 2's on the top there is actually mercury 1, as you can see here. And mercury 1 comes as a dimer of 2 mercury 1's together. That's why there's a 2 on the bottom. And this guy was just the 1, 2 is actually mercury 2. So that's kind of a weird one for some people. How do you know it is mercury 2 versus mercury 1? The 2 on the bottom for mercury 1 sticks around. So if you look at a formula like this, Hg2O and HgO. This is mercury 1 oxide. The 2 is still there on the bottom. This is mercury 2 oxide. No 2 on the bottom there. Yeah. So that 2 on the bottom tends to stick around with the mercury 1 in the formula, and you could kind of see it on the bottom. And again, that's how you could kind of tell that it's mercury 1 versus mercury 2. Any questions on that there? All right. All right, so as we talked about, we're going to use Roman numerals to indicate the charge on the metal. And once again, everything else kind of named the same as previously. So let's take a look at some examples. So take a few moments, give the names for each of these on the left and the proper formulas there on the right. See how you're doing. So again, always want to kind of identify what you're dealing with. So CO, which is cobalt, which is a metal, and Cl, which is chlorine, which is a nonmetal. So once again, that should check off for you the ionic box, and really always the metal most important. And when we look at the CO, we can see it in the dead center-ish to the right there of the transition metal region. So that should kind of check off for you. Oh, let's say type 2. I do need to use a Roman numeral, and I do need to figure out the charge of it. So you could roll through it however you want to do that. But again, just drawing it out sometimes is easier. I do know Cl is group number 7, which means it should have a -1 charge. And once again, there are 3 of them, which would give me an overall -3 charge. And that would mean that my cobalt in this case would have to be a +3 to balance it out. At that point, you now have everything you need for the name. We're going to go whole name of our metal, which is cobalt. We're going to Roman numeral A3, once again, not for how many metals we have, but for the actual charge on the metal. And again, it does not matter how many of those nonmetals you have. We are just going to use the single name for it, which is chloride in this. So cobalt 3 chloride. Any questions on that name there? Coming to our next one, we see Cu, which is copper, a metal. I, which is a non-metal, so checking our ionic box. Copper is a transition metal, which is checking our type 2 box of I need a Roman numeral. So now we can roll to figuring it out. So copper with not sure the charge. Once again, iodine is group number 7, has a -1 charge. So in this particular case, our copper must have just a +1 charge to balance it out. And now we could go to our name, whole name of the metal, which is copper. We're going to Roman numeral 1 for the charge, and going to do an iodide on our last part there. Any questions on that one there? Here we have SN, which is tin. That is a metal. Br is bromine, which is a non-metal. That's going to check the ionic box off. Once again, here, tin is not a transition metal, but it is one of those ones to the right underneath the staircase that basically also has variable types of charges. So we do need to check the type 2 box for that guy. So our tin here, not sure of the charge, but I do know if I take a look at the periodic table, bromine is group 7, and there's not one of them, but there's actually 4 of them hanging out. And that gives me a 1, 2, 3, -4 charge, telling me that my tin must have a +4 charge to balance it out. That's going to give me a tin Roman numeral 4 because of that. And once again, here, doesn't matter how many, it is just going to be bromide at the end. Any questions on any of those names there? All right, so going from our name to our formula, a couple of things to jump out at you. We do see Roman numerals, so we know we are dealing with an ionic compound, and we also know we're dealing with a type 2 ionic compound that has a metal with a variable charge. The good news on this is there's nothing for you to figure out because it kind of just tells you. So when it says iron with a Roman numeral 3, because the Roman numeral is the charge, that means I already know my iron has a +3 charge because, again, that is what the Roman numeral means. Oxide is oxygen from the periodic table, and that is group number 6, which is a -2 charge. So now we just need to put ourselves together here to equal 0. And again, 6 is going to be a common number between them. So to get the oxygen to 6, we will need 3 of them. And to get our iron to 6, we'll just need 2. So now that gives us our formula. There's 2 irons and 1, 2, 3 oxygens. And now we have our proper formula in this case. Any questions on that one there? Nickel, Roman numeral 4 chloride, again tells me I have a nickel that has a +4 charge because of the Roman numeral. Once again, here, chloride is group number 7. It's a -1. Again, to put this together, 4 looks like a number that will do that for us. So actually here we just need to get the Cl, the 4, and that means we need 4 of them. That's going to give us a -4 to balance out our +4. I'll come up here. That's a nickel with 4 chlorides, right, in this case. Lastly, tin Roman numeral 2 phosphide. So tin is Sn. And obviously a Roman numeral 2 means it has a +2 charge. Phosphide is phosphorus on the periodic table, which is group number 5. And again, group number 5 has a -3 situation. And again, here 3 and 2 is 6. So to get our tin to 6, we need not 1, not 2, but we need 3 of our tins. And we need just 2 of our phosphorus. So 1, 2, 3 tins. Actually, we go over here. 10. And 2 phosphorus in this case. Go. So we end up with our 2 phosphorus. Any questions on any of those there? All right. So difference between type 1 and type 2. Type 2 needs a Roman numeral. How do you know you need it? Again, it's really the metal that tells you whether or not you need it. So that's what I was saying earlier. The metal is really the most important thing. The metal is really going to tell you, do you need a Roman numeral or not? And if it's a fixed positive charge, no Roman numeral needed. If it is not a fixed positive charge, then you are going to need that Roman numeral. So again, that's really why whenever a metal's involved in anything in terms of naming, that's really what kind of determines, the outcome of the name. And really what you're determining is that piece of information, should you put a Roman numeral in or not, basically. Any questions on that there? Okay. All right, let's get those. Here's a little decision tree, what we talked about. We're going to now talk about type 3 binary compounds. We've talked up to this point that if we have a metal involved, we do not want to use a prefix, and you should not use a prefix, and people love to use prefixes all the time. So the good news is this is where we should use prefixes. So with type 3 compounds, This is where we use prefixes. And type 3 compounds are different than type 1 or type 2 because they are two nonmetals. And as we talked about with bonding, we got sharing of electrons, and we have a covalent bond, or these sometimes referred to as a molecular compound. So here we actually have sharing of electrons. We do not have ions, and we do name these guys differently. Now, as I mentioned before, this is typically where we use prefixes. And prefixes like mono is 1, di is 2, tri is 3. There's a table coming up with all these on it. Tetra is 4. Penta is 5. A little hexa is 6. A little hepta is 7. Octa is 8. Maybe like a nona is 9. Perhaps a deca is 10. Sounds good. So these are the prefixes that we use. And here's the deal. We basically should be the easiest things that you name. And these should also be the easiest things that you write formulas for when you have a type 3. I will say, with that being said, this is also the ones that people screw up the most on because they go, it can't be that easy. I want to do all kinds of weird things and add extra things to these things. So these, you don't have to figure out any charges because there are no ions. You don't have to figure out anything other than you have to figure out how many of each element you have and the appropriate prefix. That's pretty much all you have to figure out. So when we name these guys, we always go sort of how the formula is written. So whatever element comes first, comes first. Whatever element comes second in the name. And we use a prefix if necessary. And we still use the whole name of the first element. Then we use a prefix on the second name. And the second name gets the normal kind of non-metal treatment where we add the IDE. So it's prefix if needed, whole name of the first element, and prefix IDE treatment of the second one. Now, when I say if needed, there is an important rule when you're doing type 3, which is our friend mono here. Mono is not used on the first name, but it is okay on the second. So if you have one of something, we don't use mono on the first name, but we can use it on the second name, and we should use it on the second name if necessary. The other common thing that sort of occurs, as we'll talk about, is you will at some point, because of the prefix ending, the vowel on the prefix that ends, like an O or an A, and the vowel on the element names, first letter, you will end up with two vowels that back up to each other. So, for example, you may end up with two O's that back up to each other in the name, one from the prefix ending and one from the element name. Or you may end up with a and an O that backs up to each other in the name. And again, the A is going to come from the prefix and the O would come from the element name. And we don't want to do that, so we typically get rid of the prefix vowel. A very simple example that will cover all these rules is our good friend a C and an O together. Yeah. So C is carbon, which is a nonmetal. O is oxygen, which is a nonmetal. So once again here, we know it's going to be type 3 because we have two nonmetals involved. So obviously here, we're just looking at not charges, but we're just simply looking at how many we have. So we have one carbon, which technically the prefix would be mono, and we have one oxygen where the prefix would be mono. So rule number 1 is we do not use mono on the first name. So here we don't call this monocarbon. This would just be called carbon. Yeah. So we don't use that on the first name. Now the second name, we can use mono, which is all good. So we could use mono. And now the second element gets the IDE treatment. So just like we did previously, oxygen becomes oxide, right? And now we get a name of carbon monoxide. They are not called carbon monoxide detectors. They are called carbon monoxide detectors, yes? And that is because we just got what I was talking about, two O's that backed up to each other on the name. One O from the prefix and one from the element. Here we drop the first O and we get the proper name for this, which is carbon monoxide. And again, those are the very common things that happen in a type 3 situation. So if you end up with two O's together, prefix to the first letter, we get rid of the O on the prefix. If you end up with an A and an O, the A from the prefix, we get rid of it. The one thing that's actually okay is if you get a couple I's together, two I's, people seem to be okay with that. So if you get two I's that back up to each other, we're okay. Any questions on that? Once again, no balancing anything here. It's just simply how many of each of those do you have? So as I mentioned, here's a table and some of those awkward sort of naming. And again, we want to get rid of the A or the O if they back up to each other. Now, as we also mentioned earlier, there are certain things that go by their common name. Like again, H2O is water. It is not dihydrogen monoxide. Nobody wants a refreshing glass of dihydrogen monoxide, right? Probably why they don't use that name. It probably won't sell so well, I imagine, right? So again, H2O is water, NH3 is ammonia, CH4 that we saw earlier is methane, like the stuff that comes out of the gas vent there as well. Now, one other sort of consideration in terms of two nonmetals coming together when we're naming is hydrogen. Now, hydrogen is a nonmetal, and although it is a nonmetal, we typically do not name it like a type 3. So we name hydrogen much like it's sitting on the periodic table, much like a type 1 compound. So when we go to name hydrogen, we kind of name it like a type 1 compound. So what am I talking about? I'm talking about something like this. If you had HCl in the gas phase, we again would not really name this like a type 3 with some prefixes. We would simply just use hydrogen, and then whatever the second guy is, we would use this name, and this would be hydrogen chloride. And again, we wouldn't use a prefix on either of these, even though they're both nonmetals. There's a lot of reasons for that. One of them being that a lot of these things become acids, and at that point, one hydrogen gets hydrated. It kind of acts like a ion in solution, and it's very much like a +1 kind of guy floating around. So it's named that way as well. And we do balance things out the same way. So if we had H2S, and again, if this was a gas, this again is hydrogen, not dihydrogen, but hydrogen. And this would be sulfide. Once again, the reason we have two of them is sulfur is -2. Hydrogen technically in this situation would be +1, especially if it's in the acid form, which is becomes, and we got two of them to balance it out. So hydrogen is kind of an exception. We don't really name it as a type 3, even though we're kind of really dealing with two nonmetals. It is more named like a type 1 sort of compound as you go through there. Any questions on that there? All right. All right, so why don't you name those guys? Why don't you also give the formulas for a little dinitrogen trioxide. Let's make some stuff up that doesn't exist. Let's do sulfur hexabromide. And let's do a one that definitely doesn't exist. Let's do a trioxygen. Uh, Pentasulfide. Why not? That sounds like fun. All right. There is an E at the end there. It just got cut off right there. All right, names on the left there, formulas on the right. Okay, so let's take a look. And again, like I said, these really should be probably the quickest ones that you do. Again, what you want to identify, we have an I and an O. Those are both nonmetals. So again, we do have two nonmetals. That should direct you to, it's a type 3, which should direct you to prefixes. And again, we just going to pick out what prefixes should work. I got 2, which is di. I got 7, which is hepta. And really, that's sort of all we need to name this. So we're going to go di and the entire name there of the first element. So diiodine. Here we're going to go hepta. I am going to drop the A because I got an O coming here with my oxygen. And we'll do heptoxide. Again, dropping the A off of the prefix because we don't get that A and O sort of combination. Any questions on that one there? Next one, we got a C, which is a nonmetal, O, which is a nonmetal. So once again, going to check the type 3 box. That's prefixes. We have 1 carbon, which is mono. We have 2 oxygens, which is di. Once again, one of the main rules is we do not use mono on the first name. So we're not going to use it on the first name. So we'll just use the whole name of the element, which is carbon. Here it will then become dioxide, so carbon dioxide in this case. Any questions on that one there? Next, we have phosphorus, which is a nonmetal, chlorine, which is a nonmetal, and that's going to check the type 3 box. Mono, once again, here for our 1, and tri for our 3. Again, not using mono on the first name. Once again, it is okay on the second, but not the first. So we're just going to use phosphorus. And we're going to go tri for the 3. And again, going to give the IDE to the second guy. And that's going to give us phosphorus trichloride. Any questions on any of those? Again, nothing to balance out, really. Nothing to sort of figure out charges. Just simply pick the proper prefix. Any questions? Probably the fastest of all of them that you'll ever do is on the right-hand side here. And that is if you have the name and you need to write the formula. Why is that? Because when I look at this name of dinitrogen trioxide, I see prefixes. That tells me it's type 3. That basically tells me I don't need to figure out anything but write what it says. So nitrogen's a big N, and di means 2. So I put a 2 on the bottom. Tri is 3 and oxide is oxygen, so that's an O3 and I'm done. I don't have to balance anything, figure out charges, basically just write what's there. Same thing here. I do not see a prefix here, but I do see a prefix here, and I know that the only place prefixes should happen, type 3 situation. So when I don't see the prefix on the first name, I know there's only one of them because we don't use mono on the first name. So that makes it really simple. I write an S. And hexa is 6. And bromine or bromide is Br. And I'm just going to put a 6 on the bottom. And I am done in that case. Yeah. And lastly, here on whatever I made up here, tri and penta, some prefixes. So tri is 3 and oxygen is O. So we're going to O3. Penta is 5 and sulfur is S. So, whatever that may be, probably nothing. Would be O3 S5 in this case. Yeah. Any questions on this one? So again, type 3 is the only place where you use prefixes. At this point, you should see that there is no mixing things together, right? There's no like Roman numerals and prefixes together or anything like that. So again, you should not, in any case, usually be mixing those things. If you're like just prefixing it up and Roman numeraling it up, should maybe also put an X on it as well. That may save me some time because that probably should not be the situation. Any questions on type 3 there? Okay. So again, type 1, ionic compounds, metals, nonmetals. The deal there again is fixed positive charge there on the metal. Again, what that basically means is no Roman numeral, whole name of the metal, IDE for the nonmetal. Type 2, also ionic compound, metal, nonmetal. Deal there is metal can have multiple charges. So you need to figure out what the charge is on the metal in that situation. And that is what the Roman numeral indicates, the charge on the metal. whole name of the metal, Roman numeral for the charge on the metal, IDE for the nonmetal. And type 3, as we just went through, covalent compounds, molecular compounds, sharing of electrons, no ions involved. Basically, this is where we use prefixes. Just need to figure out how many of each you got, use the appropriate prefix, and just watch out on those little things like no mono in the first name, no two O's, no A and an O in the name, and you should be in good shape there. Yeah. Any questions on that? All right. I think that's a good place to stop.